the Sustainability Management Master's Program, you're answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact. The final session of the Spring 2025 Sustainability Seminar Series. So this seminar is sponsored and organized by the naming sponsor of the series, Hugo New Corporation. So we have among us Dominic Luikenhoff from Hugo New Corporation. Dom is a very good friend and is known to many of you already as he manages the Hugo New sponsorship of the seminar series and is here at least once every semester. Thank you, Dom. So she is the Executive Vice President of Corporate Affairs and Sustainability at Hugo New. She leads the company's global efforts in corporate sustainability, health, safety, and environmental initiatives, public and community affairs, and green business growth and investment. Dom also serves on the board of advisors of our School of Engineering and Science. So prior to joining Hugo New, Dom served as a senior advisor to the EPA Region 3 administrator. She has a MS in microbiology and biophysics, and she was a National Science Foundation Fellow. So Dom will introduce today's speaker, Brian Burzon, who is the co-founder and CEO of Clear Energy. All right, all yours, Dom. Welcome, Brian.
Okay, thanks, Dibs. Just to share with Brian, we always save the best for last. This is exciting for the students because I think it's this is about it, right? It's the last seminar, and school is moving into
wrapping up.
Final countdown. So to celebrate that and to sort of introduce our seminar today, before turning it over to Brian Burzon, who you just heard, will be speaking about Fusion Reimagined, how Thea Energy's Stellarator breakthrough could power our sustainable future. I'm going to turn it over for a quick quiz that I think Div said he's giving you like 50 extra points if you make 100 on this or something like that. It's the fusion versus fission energy face-off. So let's see how many of you guys can get these. These are pretty easy. If anybody wants to raise their hands, or we'll just pretend like we heard you in the interest of time. So what is the main difference between nuclear fusion and nuclear fission? Is it A, fission splits atoms, fusion combines them? B, fusion splits atoms, fission combines them? C, both create energy by burning fuel? D, fusion uses fossil fuels, fission uses electricity. What's the answer? Anybody?
All right, so Preet, go ahead.
Preet.
Yeah, thank you, Professor. Dominic, I think it's option A.
Well, that's correct. Very good. You get 20 points. I love playing with Div's class. All right, number 2. That one's giving me a hard time seeing it. Which type of nuclear energy powers the sun and stars? Is it A, fission, B, combustion, C, fusion, or D, radiation?
Well, a lot of people are writing stuff there and they're all right. They're all
Well,
talking about C.
well, I'll say we got a winning streak here. So
Yeah.
50 more points out there. All right, number 3. Why is nuclear fusion considered a holy grail of clean energy? And this is something that I am, as a career environmental protection specialist and focus on sustainability, this is what I am especially excited about, to hear from Brian Burson today about the state of fusion. Why is it? What's that? Is it A, it's cheaper than solar? B, it produces zero waste and uses coal? C, it uses abundant fuel, creates less waste, and has no meltdown risk? Or D, it's already widely used in power plants? Answer?
Siddharth?
C.
That's correct. It's C. Wow, another 20 points. And finally, last question. What inspired the name Stellarator for the early fusion device developed at Princeton? Was it A, it was shaped like a star? B, it aimed to recreate the fusion reactions inside the stars? C, it was named after the inventor's sister Stella? Or D, it was powered by starlight?
Supreet?
I think it's B, option B.
Wow, Supreet, you killed it. That's it. With that, I think we're going to turn it over to our speaker today. And just briefly, you heard about some of Brian Burson's background. He's the co-founder and chief executive officer at Thea Energy. Has a diverse background as both an operator and investor. He brings a unique blend of technical expertise and entrepreneurial vision to the fusion energy sector. Prior to founding Thea Energy, he held roles in electrical engineering and venture capital, providing him with a comprehensive understanding of both the scientific and business aspects of energy innovation. Under Brian's leadership, Thea Energy has developed a novel approach to stellarator design, utilizing planar electromagnetic coils to simplify construction and enhance scalability. This innovation aims to overcome traditional challenges in fusion reactor design, positioning Thea Energy at the forefront of the quest for sustainable and abundant energy sources. Brian is a recognized thought leader in the energy industry, having spoken at prominent events such as CERAWeek, where he discussed Thea Energy's approach to commercializing fusion power. And with that, I'm very appreciative, and we're very honored to have, we know you're very, very busy these days. It seems like now that I'm focused on fusion, I get feeds every day in terms of what's going on with fusion energy, Brian. So very excited that you can join us. I'm going to turn it over.
Hey, Brian, before you begin, and Dom,
Yeah.
You probably know our VP of Research and Innovation, Edmund Sinokowski. I actually he used to work in Princeton with Gates, David Gates.
Yeah, that's right.
So he basically said that he wanted to be here, but with his schedule, he couldn't.
I
So
believe it. Well,
yeah,
give him our regards, especially Dave. It's
he will
definitely
do.
been a couple of years, but great to hear that.
Please.
And thank you, Dom. I appreciate that warm introduction. I appreciate our relationship that we've developed over the past, what is it, year and a half after being at Kearney Point, and very excited to talk about what's happening at Kearney Point, literally as we speak, with some engineering talent from Stevens. So it all really comes full circle there. Excuse me for 1 second. I'm just gonna take over the screen share. And I mean, at this point, you've already had a Fusion 101 crash course here, so I don't really have to do too much work. But over the next half an hour or so, I'm excited to tell you more about what we're working on at Theia Energy and why exactly fusion is the holy grail for energy. So stepping back a second to the state of the world and the energy needs of humanity, they're pretty big and they're growing rapidly. And there are a couple of things on the left-hand side of the screen that we've actually had on the slide for quite some time. And there's a newcomer of how this industry, as in power, the biggest industry in the world, one that we all rely on to live, has crept up and emerged and is forecasted to be the equivalent of multiple European nations in terms of the output power requirements in just a few years. So as we stand in over the past 20 years of electrification, there is no single source of power, of electricity, of thermal power, all those different types that achieves the goals of humanity to power our daily lives, to make steel, to create industrial heat. And that has been an unsolved challenge, and challenges are opportunities. So over the past couple of decades here, you've seen mass adoption of solar and now battery storage, of fission. And now we're at a tipping point where even those solutions are not enough to power the future of humanity, where the global electricity demands of the world are forecasted to double in coming decades. And of course, on the right-hand side of the screen, this box of AI and ML. Just over the past really 24 months, you've had this emerge, and you've had the likes of Microsoft turning on 3 Mile Island again. The need for power is driving people to look in new areas, and also driving people to think about costs and timelines to commercialize the technology in a completely new light. And of course, fusion can uniquely solve for these things. So as Dom was mentioning before, fusion is very different than fission. Fusion uses the most abundant element in the universe, hydrogen, to manufacture energy, and to do so on demand with no risk of meltdown or incident, with minimal proliferation risk, and with no long-term radioactive waste. So fusion has been, before I was born even, the holy grail. However, making fusion is really, really hard. We'll talk about that in a second. The sun does it very well. The sun currently has a monopoly on it. And there are a number of companies, Theia Energy included, that are working to commercialize fusion energy here on Earth as a source of power and electricity. When fusion gets commercialized, and this really is a when, not an if, at this point in time, there are an order of about 50 companies working to commercialize fusion. I would wager that it's not even just one company that commercializes, it's multiple different types of technologies that get commercialized to make fusion, including, of course, the Stellarator, our flavor of fusion, which I'll tell you more about in a second. But when fusion gets commercialized, it changes the way the world works forever. Fusion can uniquely power the energy needs currently faced by humanity in 100 and in 1,000 years. And while doing so, it changes really the fundamentals that underpin society. If you look at really the history of geoconflict over the past, I would point to 20 or 30 years, but you really don't have to look more than a few years back to see Europe, the global north, brought to its knees because of reliance on Russian oil and gas. So energy is geopolitics, let's be clear about that. The world, which has about 8 billion humans on it currently, 1 billion humans don't have access to reliable electricity. So this is an energy currently inequity situation. And of course, climate change. We can't not talk about that. Decarbonization is a significant challenge that is also unsolved. And by manufacturing fusion energy, you can uniquely make a carbon-free source of power for the future. So fusion will change humanity forever. Okay, I guess I'll have to do a Fusion 201 course after Dom's 101, but we'll keep this brief. Fusion in the sun uses hydrogen, shining bright today. It works very well. It has immense gravity, has a lot going on for it. Here on Earth, the equation is slightly different, where our flavor of fusion, we create pretty much a magnetic bottle to confine a plasma, a fusion fuel, in a very specific configuration. And with that, we superheat a ionized form of gas known as a plasma to manufacture fusion here on Earth using a mix of deuterium and tritium. So you need to get plasmas really, really hot. Cool thing about this is it is so energy dense. To power downtown Manhattan for a year, it would be mere liters of water. And that's really hard to comprehend, just how much the equivalent oil and gas or coal is. Fusion takes the lightest and most abundant element in the universe, hydrogen, and uses it. It's Einstein's E = mc squared. By a small decrease of mass, you have a tremendous output of energy. The way that fusion is done here on Earth is in magnetic bottles, the tokamak and the plasma being the best studied of the two, and inertial confinement, which is usually with lasers. You may have seen just a few years ago, NIF, the National Ignition Facility here in the United States, actually achieved ignition, not just once, a number of times. So there's some really exciting stuff happening across the board, across different types of technologies in fusion at rapid pace over the past 5 years. Fusion is coming, and it's really not that far away. So our flavor of fusion is that one in the middle, that's Stellarator. The Stellarator and the tokamak, which is probably one that you've heard of, are the most studied forms of fusion, and specifically of magnetic confinement. So we use big electromagnets to confine a plasma, a fusion fuel, in a very specific way. And the tokamak and the Stellarator both have a magnetic field in the long way around the donut, the toroidal magnetic field, and you make that via the encircling coils, the things that surround the plasma and ring. The real difference between the tokamak and the Stellarator is how you create the poloidal magnetic field. So a pole-to-pole shift, twisting that. In the Stellarator, you are actually twisting the entire device itself, which creates some advantages, but it also creates some disadvantages. There's no such thing as a free lunch. In the tokamak, very similarly, you drive current through center solenoid and poloidal field coils. You drive energy into the device. The advantage there is that every slice is symmetrical, and therefore it's much easier to build. The disadvantage is that you have to put energy into the device to make it run. And if you consider a power plant, the goal of a power plant is to put energy on the grid, not to push energy into the device itself. So it's just a mismatch of energy balance. But diving in on the Stellarator here, this device creates a really nice plasma. It's called magnetostasis. It's a steady state plasma, happy in that very Mobius strip-like orientation. However, of course, the trade-off here is the engineering challenges of making a device that looks like that. And we'll talk about that more over the coming minutes. So the Stellarator is very specifically 70 years old. As Dom was referencing, it was created by the founder of Princeton Plasma Physics Lab in the 1950s. His name was Lyman Spitzer. And while he might be lesser known for creating the Stellarator, he is also known for proposing the Hubble Space Telescope. So was really the father of fusion research here in the United States, as well as space astronomy. Big deal and well ahead of his time. And at Princeton Plasma Physics Lab, PPPL, and a number of other institutions across the world, the Stellarator has been furthered along. There have been very large-scale integrated systems that have been built that prove out the science of this technology and give us codes that are peer-reviewed and benchmarked against system performance, and give us computational tools to really understand the physics balance of it, and to allow us to focus on the engineering challenges of the device. And that's really where startups thrive. Academic institutions like Stevens and Princeton, they're great at furthering scientific knowledge of humanity, and private industry startups are great at taking that baton and pushing forward towards commercializing a product. So Theia Energy is around 2.5 years old. So one of the newer fusion companies out there. There are quite a few that have been around for close to 20 years at this point. But that enabler of the work that was done at Princeton Plasma Physics Lab really only turned the corner in 2022 as part of an ARPA-E project that allowed us to think about new ways to build the hardware for this device. So 2.5 years in, we have about 60 employees. Already outdated this slide since just a few months ago, so we've grown a bit even since then. 60 employees. We're based in Kearney Point, New Jersey, and we have our labs there where we design, manufacture, and operate superconducting magnets and fusion hardware. So in New Jersey, not too far away from Stevens, are probably the coldest temperatures in the tri-state region, going down to 12 Kelvin, 12 12 Kelvin off of absolute zero, so very, very cold conditions. And also probably the strongest magnets in the tri-state area as well, now well over 5 Tesla. So some really interesting, great stuff happening in Kearney, New Jersey. Over the past 2 years since we formed, we raised our Series A. That has allowed us to get into hardware mode. We were selected as one of the awardees for a DOE, Department of Energy milestone program towards the commercialization of fusion power plants here in the United States. And we've built and scaled a world-class team. So the reason that my co-founder David Gates and I founded Theia Energy and came up with a new approach to the Stellarator has to do with some of the shortcomings of this device. Although it makes a very great plasma physics basis for a power plant, the engineering challenges associated with these magnet systems are pretty immense, to put it mildly. This is W7X. This is the best performing Stellarator in the history of the world, currently operating in Germany. And this device, it's a true feat of engineering, it's a true feat of science, and allows us a lot of those computational tools that I was mentioning that create a path to commercialization. However, it really also highlighted this Achilles heel of the Stellarator, that the complexity and the precision required for twisting that device in that Mobius strip orientation means hardware is hard. And this is a pretty universal rule spanning fusion, aerospace, and anything in between, that the more complexity and the more precision that you have in hardware, usually the more expensive and time consuming these systems become. And to characterize that, W7X went about 3x over budget and took 10 years behind schedule, beyond what they thought. And that's okay for a national lab and academic institution furthering a science, furthering humanity, furthering knowledge. But when you consider what fusion has to be when it grows up a power plant, that is unacceptable for industry. Utility scale devices here in the United States need to be built on time, on budget, so you can scale an industry and effectively have a business model for the end users, the utilities or owner operators, and all the various players in terms of procurement and construction. So risk is bad, complexity is bad. These are very firm rules of the energy industry. And so fusion coming up, great technology, great science. There is an interface that really must align, and therefore fusion must create an architecture that is capable of scaling via typical energy and industry means of building and operating power plant devices. And so what we've really done at Theia is we've attempted to take as much of the complexity and precision out of hardware and transfer it onto the control systems on the software stack. Software is scalable. Software, you build it once, it works on the 100th power plant all the same. So we really love a software-centric approach because it's very capital efficient and very scalable. And the real thesis for this is we have, in essence, made an array of magnets that I usually think about like the pixels in the computer screens that you're all staring at right now. In the computer screens that you're staring at, there are probably 2 or 4 million pixels, quite a few of them. And they're all actually identical. They're all the same. But via a control system, via your computer, every single one of those pixels is controlled individually. And therefore, you can see the really high resolution images on these screens. And that's great. So what in essence we have done for the Stellarator is we've made an array of magnet pixels. We don't change light, we change current and therefore magnetic fields. And we can create really precise, really high resolution magnetic fields that are required for Stellarator systems, but without the complicated hardware. So right away, we got around the biggest constraint of the Stellarator, being able to use simpler hardware, more complicated software for sure, but that's something that we'll take in spades. We have a really great group of electrical and control systems engineers that have built out the software stack already that we need. What this has also allowed us to do is to have some really important practicalities to the long-term operation of a power plant. And where we sit in New Jersey and really across the country, when you look at the traditional industrial norms of building utility scale power, a power plant, a lot of the work is done by local trade laborers, people pouring concrete, setting rebar, bolting things together, lots of welding. When you consider what's happening within the walls of a fusion device, it's a bunch of Stevens engineers and a bunch of MIT physicists, and that is great for building your first integrated system. But when you think about scaling 10 or 100 power plants across the world, and you consider how a technology must be adopted to work within those confines, those traditional industries, you start to say, okay, well, that isn't scalable. And software pretty uniquely has solved this for us as well. Because when we consider a power plant that gets bolted together in New Jersey versus the other side of the country or the other side of the world, we pretty much are assuming that there's going to be variability. That is the baseline, and even at a culture at the company that we assume. We don't want to rely on perfection. And that's pretty tough because most of fusion to date over the past 70 years has been let's assume perfection exists to try to make these fusion conditions. We take a very different approach to what we think that the norm of society and the norm of building and operating power plants for decades on end is going to be. And therefore, from that baseline, we assume that some things are going to be just mismanufactured, and some things are going to be put together slightly incorrectly. And you better have a way to solve for that. And the software uniquely allows for that, because over every single magnet in our array, which is about 450 in this grid that envelops the system, we can now fine tune out this noise, this variability. And perhaps this means that we don't have to manufacture every system component to the 0.001 millimeter that is so very expensive in hardware. Or maybe what this also means is that when something just gets bolted together on site and it's slightly off axis, we now have a way to tune that out within the control system to be a little bit more hardware agnostic. The real driver for this, though, was what happens over the lifetime of a power plant, where a system will have wear and tear. I drive to work every day. I've had to replace tires, oil changes, those type of things. Cars get wear and tear. Power plants are the same. And over the lifetime of an asset, which is a very long time for a power plant, much longer than a car, if you can have a way to tune out that wear and tear and have a device that continues running with a high capacity factor that doesn't need to go offline for maintenance and have pieces of machinery repaired, replaced, capital expenditures, that's what works. That's what sells. That's what keeps on making power day in, day out. And we were sitting there really in 2024, just last year, and thinking about this and said, light bulb moment. The software stack not only does it allow for the simpler hardware to begin with, it allows us to fine tune these variables over the lifetime of operation. Every single magnet in this array just has a ton of data sensors that we get out and we put into our controls models. And really, actually, in the past couple of months within our labs in Kearney, we've mismounted magnets, we've started to break magnets, and we've shown that even without us there sitting there turning knobs, the control system at this point, it's closed loop. So it really identifies faults or changes and can optimize those out on the fly with very little involvement. We see that as what really scales to build power plants that keep on working, that keep on making power in a capital and energy efficient manner, and ultimately scales across the world to make a lot of power in an efficient way. Well, I got to talk about this one as well. Not only is AI a great use case for power demand, AI actually is a big enabler for having better systems as well. So within this architecture, within our array of about 450 magnets, this is like the perfect sandbox for AI. AI is really good at interpolating across data sets. Every single one of our magnets has about 45 data instrumentation readouts from it. So 45 magnets times 450, or it's a big number, and it's more of an exponential as well. So we just have this immense data set from coupled inductance models and all the different data readouts from the magnets that allows us to already train AI and machine learning models that will really allow for a constant reoptimization of the device long term to have it operating flawlessly, even though all these different variables of wear and tear and real world scenarios come into play. So over the past year and a half, 2024 into 2025, we have made great progress prototyping these core technologies, designing, manufacturing, and operating superconducting magnets, and now an array of superconducting magnets where we can show the viability of the control system, all within our own walls. So we have about, as I mentioned before, those 60 physicists and engineers. We've been doing some really great work, some really hard work. Hard work is hard, let's be clear here, but it's ultimately the most rewarding thing that I've ever been part of. And we've been taking those kind of building block technologies and starting to integrate them to be a large scale device that is capable of making fusion energy. We call that device EOS. We're really big into Greek mythology here at Theia Energy. Obviously, Theia is a Greek goddess of divine light, and her children are Eos, Helios, and Serene. So the dawn, the sun, and the dusk. So therefore, our first device is the dawn. It's not a power plant, it's slightly subscale, but it's an integrated device based on our technology that will make a decent amount of fusion energy and do so in steady state. So we see this as the key enabler, the key de-risk to show that you can make fusion energy in a reliable, efficient way. This device was the next 5 years of our life. We have a great integrated design of it, which I'll show you in a moment here. And over the next year or two, we're going to be looking to put the shovel in the ground to start constructing this facility. This facility, as I mentioned, will make fusion energy and will do so in steady state. From there, it will be about scaling this technology to make multiple of them to put fusion energy on the grid in the form of power plants. Going back to the Greek naming, of course, the dusk, I should say that the dawn is first, the sun is next. So Helios, our first power plant, is something that we'll plan to put online in the early 2030s following EOS, as it is a scale-up, bigger system, but the same technology, the same architecture, and that one will be on the grid producing electricity. We're really excited about that, and we're really excited that to commercialize fusion for our technology, there are no miracles required. There's no new science that we need to do this. There's a lot of hard work. There's a lot of good engineering of the varietals that Stevens has: mechanical engineering, electrical engineering, systems engineering, program management. It's a lot of hard work, a lot of blocking and tackling, but things that humanity knows well. So here's a quick rendering of the EOS integrated Stellarator facility, at least the outside of it. We're really excited to talk more about this really in the coming weeks, so stay tuned. This is something that we've been working towards for really since we founded the company. And later in the second quarter here, we're going to start more openly telling details, expressing some very interesting points about this next phase of company growth to build this device, to build this integrated system, which shows our technology within commercial relevancy. And to wrap this up, and I'm excited to get into some Q&A here. I want to make sure we have some time for a great conversation. Wanted to just share this quick page on our hiring. We are rapidly growing the company. This is everything from internships to full-time and very experienced positions late in career. We have a job board on Lever. There's a link and QR code below, and we can make sure to get this information back to the team at Stevens here. This is something that even if there's not a job posting currently, stay tuned, because hiring is very continual and fluid for us. So even though there might not be something today, there might be something in a month or a few. And across the board, we're hiring in operations and HR and some other functions there, to pretty much every type of engineering. But of course, want to highlight control systems engineering. I mentioned the software before. We're doing a lot in the software development side of the world. We're building superconducting magnets, that we're hiring magnet engineers that span mechanical and electrical engineering, as well as some test engineers that are actually in the lab building operating devices with us. So please do reach out. Please do follow up and submit an application to any one of our job postings, and we'd love to continue the conversation now and into the future. So with that, happy to open this up and just have a conversation here.
Cool, thanks, Brian. That was very, very informative. As you can see, a bunch of hands are raised.